All right, we're going through an introduction to simple linear regression. So far, we've done a bunch of stuff. What have we done? Well, we learned about the simple linear regression model, y equals alpha plus beta x plus the error term epsilon. We learned about the regression equation, the expected value of y given x, or conditional expectation, which is alpha plus beta x. We learned about our estimated regression equation, y hat equals a plus bx. We learned how to estimate the least squares estimates of b and a. B is the sum of xi minus x bar times yi minus y bar all over, and that's the sum across every observation, all over the sum across every observation of xi minus x bar squared. We learned about how to estimate a, or alpha, how to calculate a. Once you've done this, it's y bar minus b times x bar. We learned about the total sum of squares, right, which is the sum of yi minus y bar squared. We learned about the sum of squares due to error, which is the sum of yi minus y hat squared. And the total sum of squares due to regression, or the sum of squares due to regression, which is the sum of this is y hat I, by the way, y hat I minus y bar squared. And last but not least, the last thing we learned really was how the r squared relates to these. So r squared is SSR over SST, which is equal to 1 minus SSE over SST. So there's a lot there. I walked through it. I recommend watching the other videos if you still need a little bit of work on these. But it all should be pretty straightforward once you practice a few of those practice problems. They really do a lot of good in making this stuff clear. Okay, now all of this stuff is predicated on some assumptions. In particular, we have assumptions about. We talked about one assumption, right? That there's a linear relationship, but we have assumptions on the error term. And what are our assumptions on the error term? Well, we're assuming that epsilon, which is our error term, is a random variable with a mean of 0. The expected value of epsilon is 0, meaning on average, the error is as high or as likely to be above 0 as it is below 0. And that it's centered around 0. We're also going to assume that the variance of epsilon is given by sigma squared, which is the same for all values of x. So we have identically distributed errors. And the variance does not depend on x. In addition, we're assuming that the epsilons are independent, right? So that every time you have a new observation, the error term is unrelated. And this is especially going to be violated with most time series data. So if you're looking at the same thing over time, right, like a stock price for one company, those are not independent observations. This is less likely to be violated with cross-sectional data. When you're looking at lots of different people over simultaneously, like a snapshot. But it's still going to be likely to be violated whenever you have correlation between your observations. And last but not least, we're assuming that the epsilons are normally distributed. Now, some of these are more important than others in terms of what we get. But you can see that these are kind of heroic assumptions in lots of ways. Again, we're assuming that the relationship between between x and y is linear. That one's not that big a deal because you could always just use a different model where y equals, for example, alpha plus beta x squared plus epsilon, and then you just redefine x as x squared. And we'll deal with a lot of that stuff later. But the implication of these assumptions are, well, one, given xi, right? So given an individual value of x, we know that the expected value of yi given xi is going to be equal to alpha plus beta x. The reason for that is that this cancels out the epsilon part. So that takes care of that. The other so that's one implication of our assumptions. The other one is that the variance of y is that except for epsilon, it's a this should be equals. This is a deterministic relationship, right? So except for the epsilon, the relationship between y and x is deterministic, which means that the variance of y is equal to the variance of epsilon, which is equal to sigma squared. As a result, what these assumptions really turn into is that for every given value of x, y is a normally distributed random variable. Pen is slipping a little bit. So it's a normally distributed random variable with mean alpha plus beta x and variance sigma squared, right? That's what this is implying, right? That y is always being drawn from a normal distribution with a constant shape, right? With a constant scale, whatever that's variance, constant variance, and then the mean just changes just shifts in one direction or the other with x through beta, right? So when x equals 0, y has a mean of alpha and a standard deviation of sigma, and when x equals 1, y has a mean of alpha plus beta and a standard deviation of sigma. When x equals 2, y has a mean of alpha plus 2 beta, and so on and so forth, right? So we're just changing the mean. If beta is positive, then the mean of y marches to the right. If beta is negative, then the mean of y marches to the left, but it's moving it, just along with x. Question is, we don't know what the standard deviation is, right? So we have that very common problem. We don't know the population standard deviation. But we can estimate this. If the standard deviation is large, it means that noise is a big deal. The errors are driving the variation in y. And it means our estimate is going to be very imprecise. What it also means is that we can't really know that our relationship is a good fit, right? If we have very large standard deviations. So we have point estimates of beta, of alpha and beta. How reliable are they? Well, that's where we get into testing for significance. And when people run regressions, often this is the first thing that they look at. So, testing for significance. Well, essentially, if our estimate for beta is 0, that means that there's no relationship between x and y. Right? Just that our best guess for the expected value of y is just alpha. What we really want to know is the true underlying relationship between x and y in the population. There are two tests that we commonly use. The t-test of individual significance and the f-test of joint significance. The only one I'm going to talk about for now is the t-test of individual significance, because for the f-test really only gives you any benefit when you have multiple regression, because otherwise it just gives you the same result. The t-test is the test that any individual coefficient is significantly different from 0. The f-test is the test against the null that all of your coefficients equal 0. And that's the basic value that these provide. One problem before we can get there is that in both cases we're going to need to be able to estimate the variance of the error term. So we need sigma squared, or at least an estimate thereof. And so that's where we're going next. We got to do that, and then we can do our test. Okay. So to estimate sigma squared, we're going to use s squared, just like we've used before, which is going to be our mean squared error There's another name for it, mean squared error, also called the MSE. The way we calculate that is with this formula. It's going to be the sum from I equals 1 to n of our residual, right? yi minus y hat I squared over n minus k minus 1. Now, you know this top part, and you know n. K is the only one you need to know that's new. It's the number of regressors. For simple linear regression, k equals 1. K, that's a k. It's a very terrible k, but k equals 1 for now. That's just for now, because simple linear regression means we have one regressor. Oh, nuts, I lost my pen. Let's see if I can get it back. If I can't, we might have to pause briefly while I solve it. There we go. Oh, it just doesn't work with the pen. Okay, well, I'm going to try typing to see if that'll work. So, k equals 1. What this also equals is, so this is our MSE, which is equal to s squared. Now the top of this fraction is going to be the SSE. And then for now, n minus k minus 1 is going to be n minus 1 minus 1, because k equals 1, which means that this is going to be equal to SSE over n minus 2. And that's what we have for our mean squared error. N is our sample size. SSE is our sum of squared errors. Now, if you remember before, when we figured out a sample variance, we divided by n minus 1. We're dividing by n minus k minus 1 because we have to use one of our data points to get our regression done. So, in any case, we lose degrees of freedom. We'll talk a little bit more about degrees of freedom when we get to multiple regression. Okay, so what did we calculate before? Well, we calculated our sum of squared errors before. What was it? Let's look at our spreadsheet that we built. Our sum of squared errors was 253.661. We're going to divide that by our number of observations we had, which, if you recall, was 1, 2, 3, 4, 5. 5 minus 2. So this is going to be 253.661 divided by 3, which gives us our mean squared error, also known as our s squared, of 84.54, roughly. So that's our s squared. Now, in order to estimate the standard deviation of our population of errors, we're going to need to take the square root of this. Right? If we want s, and we're going to want s for our testing, we need the square root of our MSE, which is going to be the square root of that whole fraction, if you want to do it that way. Oops-a-daisy. Square root of our sum of squared errors divided by n minus k minus 1. So that's one formula you can use. For our particular case, we have the square root of 84.54, which is going to be, what does that turn into? 9.19. So that's our standard deviation of the estimate. That's what that's called. So this is our standard deviation of the estimate. It's going to be 9.19. Okay, so that's an estimate of the standard deviation, and we can move on to our tests. The first one we're going to look at is the t-test. Oops, stop that. Of individual significance, as I said. And what we always want to do in this case is test to see whether beta is significantly different from 0. So now we're back in the world of hypothesis testing. Now, if you recall, the way that I break this up is we have step 1, formulate our hypotheses. And these are always going to look like this for our t-test. They're always going to be the same. our null is always that there is no relationship. We're testing this against the alternative that there is a relationship. Which means that if we can reject the null, we can conclude that there's a significant relationship between the two. Okay, so we don't know beta, but we estimated it with b, right? B is a random variable. It'll change based on the samples, and it'll change in predictable ways, thanks to the central limit theorem. So now we're going all the way back to sampling theory. In particular, we can say the following things about B. B is normally distributed with an expected value. It's unbiased estimator of beta, so we know that its expected value is E, which is good. And a standard deviation that looks like this. Now this is a true standard deviation. Well, I'm on the next page. I'm on the next page. Sigma over square root of the sum. I'll read this out once I've written it. Okay. So B is normally distributed, and this is its shape. It's got a standard deviation that's equal to this. So this would be sigma sub B. It's the standard deviation of the regression, sigma, or the standard deviation of the error terms, divided by this square root down here, which is its, it's sort of its standardization. So if we knew sigma, we could just standardize it and use a standard normal test statistic, but we don't. So suddenly we're in a one sample sigma unknown world. Remember that? It was just like one sample sigma unknown. So what do? Well, we choose our test statistic, right? Step 3. I skipped step 2 where we choose a level of significance. Usually we choose 5%, but for these it's very often something that people just kind of have a sense of what their what their level of significance is. We choose a test statistic, and this is what we're going to use. T equals B minus beta sub 0, which is almost always 0, over S sub B, where beta sub 0 is the value of beta under the null, and we have a formula for S sub B, which is going to be S divided by the square root of that whole thing. Let me just copy and paste it actually, because it's probably just faster. So this is going to be our S sub B. It's a standard error of beta. Under the null, T is distributed with a T distribution with n minus k minus 1 degrees of freedom. And so that's what we're going to be using, a T distribution. Okay, so for the example we've been working through, let's compute the test statistic quick for step 4. Step 4 is to compute it. So let's see what we need. We're going to need a few things. Where are we? Come on. There we go. So we're going to need B, which we already calculated. If you go back and look at your notes, you'll see that it's 0.394. We can go back to the Excel spreadsheet to see as well. B is 0.394. Beta 0 is almost always going to be 1. This is the test you use if you can do a t-test if you want to test to see if there's some theoretical reason it should be 1, for example, or beta should be 1.5 or something. You can use the test statistic to test against that as well. But for now, it's always going to be, you should assume that it's 0 unless otherwise told. Okay, now we want to calculate our, we have S, which was, what was S? 9.19. I have 9.196 in my other notes, so let's go with 9.196. Let's insert below, because we also have this sum. We calculated the sum before, which is the squared deviation, the sum of squared deviations in X. We calculated that in our Excel spreadsheet to be, that's this one right here, this x deviation squared, add them up, you get 1808. It's useful to hang on to a lot of the calculations you run because you're going to be using the same numbers a lot with this stuff. Okay, so we have all this stuff. Now we can start plugging it in. Let's copy this, paste it down here if we want, and we have our test statistic is 0.394 minus 0 over 9.196 divided by the square root of 1808. What does that turn into? Well, I'll show you how we calculate it. Get to a scrap little area. Okay, so we have our S is 9.196. We have the sum of x deviations is 1808. I'm going to take the square root of that. (42.52), and we want to divide that just to get S sub B. It's got to be 9.196 divided by 42.52, 0.216. So you want to write that down. You can do that here. S sub B equals 0.216. So that this turns into 0.394 over 0.216. We want to calculate what that is. Well, we have our numerator, 0.394, and S sub B is the denominator. So our t statistic is going to be 0.394 divided by 0.216, 1.822 roughly. There might be some rounding depending on the way that you rounded. 1.822, it's close enough. And under the null, this has a k minus 1, or n minus k minus 1 degrees of freedom equals 5 minus 1 minus 1 equals 3 degrees of freedom. So that's our t distribution that we're dealing with. Now, if you look on the t table, which we can do, let me see if we can pull that up. Where's a t table? That would be handy. We're going to be looking for how many degrees of freedom? 3 degrees of freedom. And if you recall, our test statistic is 1.822. So 3 degrees of freedom, you go across, you can see that right here we have 1.638 and 2.353 is what we are. Ours falls somewhere in between there. It means the area in the upper tail is between 0.05 and 0.10. So we can write that as 0.05 is less than the area in upper tail is less than 0.10. Now these are always going to be two-tailed tests, right? Because we're testing against the null of equality. So we double it. We got to double the area to get the p-value. So we double the left side to get 0.10 is less than our p-value is less than 0.20. Now it depends on what your level of significance is, but this seems like there's not a significant relationship. The way that we refer to this is that this relationship is not statistically significant. That's the relationship between our percent of options and percent change in sales. So that's not statistically significant. That means we can't conclude that there's any meaningful relationship. We can find the exact p-value using Excel if we want. We know that our degrees of freedom is 3, and so you can do equals t dist. I'm going to have to sneeze. Hold on. Pardon me. So this is our x, which is our value of t, whatever your test statistic. We have 3 degrees of freedom. It's a two-tailed test. You can see there's a 16.7%, 0.166 is our p-value. So there's about a 17% chance that this could just be random variation. We only have 5 data points, so it's hard to get a statistically significant result. Now, if something is statistically significant, does that mean that it matters? Well, it depends. Statistical significance is really just talking about an unambiguous relationship. It doesn't mean that it matters in a broader sense. So if two things move in lockstep, but So if each year of education granted you 0.00001% increase in salary, every year exactly, and the error on that was very small, that would be a very statistically significant relationship. But it does not mean that it's economically significant necessarily. Economically significant. So you gotta pay attention, use theory, think about what the consequences of a relationship are in order to determine whether it's economically significant. All right, so that's everything we have on simple linear regression. I would cover the F-test, but we'll save that for multiple regression. But you do have the tools to calculate that now. But we'll get there. Okay, I hope you guys have enjoyed simple linear regression. I'm hoping to get some practice problems up relatively soon. But certainly, if you watch this video while you go through some practice problems, it should give you the stuff you need to work those out. So if you have any questions, shoot me an email at jjdelaney@ualr.edu, or post a comment on the board, or post a comment on the YouTube site, my YouTube account, and I will get back to you as soon as I can. Thanks, guys. Bye.